Welcome. So, today we're going to tackle a really big question in programming. How do you take a brilliant idea that's just in your head and turn it into a plan that a computer can actually understand and follow? We are going to build that bridge right now, from human thought to computer logic. Let's dive right in. Seriously, think about your favorite app on your phone. It all started as just a simple idea, right? So, how in the world did it become this actual working tool that you use every single day? Well, I can tell you it wasn't magic, and it definitely didn't start with someone just sitting down and writing a bunch of complicated code. And that right there is the secret. Before you can ever tell a computer what to do, you have to have a rock solid plan for how it's going to get done. This planning stage, it is absolutely the most crucial part of the whole process. It's where the real thinking and problem solving happens. And that is exactly what we are going to do together in this explainer. I'm going to walk you through how to create these plans for yourself. By the time we're done, you'll be able to take a simple problem and translate it into a structured plan using something we call pseudocode. Okay, so before we can write our plan, we need to get the right tools for the job. We're going to start with a few key ideas, core concepts really, that help us learn to think about problems like a programmer does. First up is decomposition. Now, it sounds kind of fancy, but it's really simple. Imagine you had to build a car. You wouldn't just start welding pieces of metal together, right? No way. You'd break it down into smaller jobs, the engine, the body, the wheels. Well, decomposition is just that, slicing a huge, scary problem into smaller, bite-sized chunks that you can actually solve. Next in our toolkit is abstraction. This one is all about the art of filtering out the noise. See, to solve any problem, you have to focus only on the details that are absolutely essential for the solution. Everything else, it's just a distraction. And this is a perfect example. A satellite photo shows you everything, every single tree, every house. It's way too much information if all you want to do is drive from point A to point B. But a roadmap, that is a perfect abstraction. It strips away all that noise and shows the driver only what they need to know, the roads, the towns, and the route. All right, let's look at our first actual planning tool, structured English. Honestly, just think of it like writing a recipe. It's a simple, numbered list of steps written in plain, clear English that pretty much anyone can understand and follow. This is like our first rough draft of the plan. So, from structured English, we level up to pseudocode. This is a bit more formal, a little more structured. It uses specific keywords you'll see all the time, like input, output, and if. Now, here's the most important thing to get. Pseudocode is not a real programming language, but it's so close that turning it into one is actually pretty simple. Think of it as the final, detailed blueprint you make right before you start building. All right, that's enough theory. Let's get our hands dirty and actually put this into practice. We're going to take a simple, real-world problem and walk through the entire process, from figuring out our data to writing the final lines of pseudocode. So before we write a single step of our plan, we need to define the information we're going to be working with. This is our identifier table, which is just a fancy name for a list of all our variables. And you can just think of variables as labeled boxes where we can store data. So for our marathon timer problem, we're going to need a box for hours, a box for minutes, a box for seconds, and of course a box for our final calculated total. Okay, here's our first step written in simple structured English. We just need to get the runner's time from the user. Super clear instruction for a person, right? But how do we make it clear for a computer? Well, that's where pseudocode comes in. Now look at this. See how that one English sentence expands into multiple lines of pseudocode. First, we use the output command to show a message on the screen, asking the user to enter hours. Then, the input command just waits for them to type a number and stores it in our marathon hours box. And we do that exact same thing again for the minutes, and one more time for the seconds. Okay, on to step 2. We have the hours, the minutes, and the seconds all stored away in their boxes. So the next logical step is to convert all of that into one single number, the total time in seconds. And here's what that looks like in pseudocode. It's a pretty simple calculation, right? We take the hours and multiply by 3,600, then we add the minutes multiplied by 60, and finally, we just add the seconds. Now that little arrow in the middle, that's really important. It's called the assignment operator. It just means calculate everything on the right side, and then store that final answer in the variable on the left. So we've done the math, we've stored the result. The last step in our plan is pretty obvious. We just need to show that result to the user. And once again, we use our trusty output command. This time, we're telling it to display a little text message followed by whatever that final number is that we stored inside our total marathon time seconds variable. And just like that, we have a complete, logical plan from start to finish. So our plan works. That's great. But is it bulletproof? I mean, what if the user enters 90 for the number of seconds? That's not a valid time. A great plan anticipates these kinds of problems. So this next part is all about refining our logic to handle potential errors. And this is where a cool technique called stepwise refinement comes into play. All it means is that we take each of our simple steps and we just break it down even further to add more detail. So instead of our plan just being enter seconds, our new, much better plan is enter the seconds, check if it's a valid number, and if it's not, ask the user to enter it again. This slide just shows the power of refinement perfectly. On the left, you see our original simple input, but on the right is the refined, totally bulletproof version. Here, we're using a repeat until loop. This thing will keep repeating the output and input commands over and over and over until the user finally types in a value that meets our conditions. It has to be greater than or equal to 0 and less than or equal to 59. This simple little check is how you build software that doesn't break. We've done it. We've created our detailed blueprints. Now it's time for the final step, the really cool part, seeing how this pseudocode plan translates directly into real, actual programming languages. This is where you're going to see just how powerful all this planning really is. Just take a look at this. On the far left, we have a simple for loop in our pseudocode. All it's doing is counting from 1 to 10, but in steps of 2. Now, just look across the columns at Python, Java, and VB.NET. Yeah, the specific words, the syntax, it's a little different. You've got a colon here, some curly braces there, but the core logic, it is identical. This is why planning is so powerful. If you can write the pseudocode, you are 90% of the way to writing the real code. And it is the exact same story for making decisions in your code. Our pseudocode, if x greater than y, then, is so easy to recognize in every single one of these languages. The specific keywords and the punctuation, they might change a little, but the fundamental idea is exactly the same. When you master pseudocode, what you're really doing is learning the universal language of programming logic. So now you have the toolkit. You know how to break down problems, how to filter out the noise, and how to build a solid, logical plan that can be turned into code in pretty much any language. You can design the algorithm. The only question left is, what problem will you solve?